Hello, Mr. Fernando Morales in class of 12U Physics. I've chosen to do my ISU on the thermoelectric fan, or also known as the eco fan. I've chosen to do my project on this fan because we have one sitting on the wood stove oven in the other room, and I've always been curious on how it works. I originally thought it worked by heat rising from the wood stove oven and catching the blades here, and it essentially turns them, but that's not the case. It actually generates its own electricity through heat. So the fan performs by drawing heat from the metal base of the fan from the top of the wood stove oven towards the center module of the frame. So let's say this is sitting on a wood stove oven. The heat will rise from the wood stove oven into here and then up to the center to its module, the white portion there. The fan is separated at the center of the frame into two portions by a generator module. The top metal portion of the fan, comprised of fins, draws cooler air from behind the wood stove oven towards the center of the fan and the module. So the top portion, the fins here, will draw cooler air, and the bottom portion will draw hot air from the wood stove oven, and they'll meet at the center there. The generator module is comprised of two dissimilar metals, resulting in semiconductors. The semiconductors are known as eccentric semiconductors, defined by metals being doped with impurities. The semiconductors used in the module have both P and N-type semiconductors. P-types are generally thermoconductors with aluminum, and P-types with arsenic and phosphorus metals, generally for eco fans. So in this page here, we can see that on the bottom of the page, it's separated by a hot side, and then in the middle there's the two semiconductors, N and P. Those are metals, but it's all one. And the top portion is the cold side, so heat will travel from the bottom portion through the semiconductor and then touches the top portion, and then this creates an electromotive force. We'll get into that right now. The thermoelectric fan relies on the phenomena that is thermoelectricity, discovered by the Seebeck effect. The Seebeck effect was discovered in 1821 by Baltic German physicist Johann Seebeck. The Seebeck effect states that when two dissimilar metal conductors are maintained at different temperatures, which is happening in this right now from what I've explained, it produces an electromotive force. The thermoelectricity converts heat to electricity. Since the generator module is now experiencing two large varied temperatures within two dissimilar metals, this sets the module in electric contact and produces an electric field. Electrons generally from the flame of the wood stove oven travel up to the base of the fan towards the center of the fan into the semiconductors of the module. The electrons flow from junctions where they are less bound into a more binding junction. The electron flow produces an electric current, which is absorbed by the motor, converting the electricity into mechanical energy. This mechanical energy rotates the impeller of the fan, thus rotates the blades of the fan. So, electrons flow from the top portion that's heated, touches the two dissimilar metals, which are the N and P types, phosphorus and aluminum, say, and then touches the cooler fins. This separates the electrons and creates an electric field, an electric force, and then the wires, you can see, collect that. You can see the wires there. It collects that electricity and goes into the motor or rotor, and then it, in theory, basically rotates the blades. So, this circuit must be open in order to produce an electromotive force. If the circuit is closed, there are no two contact potentials to oppose each other. The Seebeck, however, does not produce a large amount of electricity, and thermoelectric production is considered to be less efficient and more expensive than other means of producing electricity. Thermoelectric power generation is generally the case of a byproduct or waste of another form of power generation. However, in this case of the electric fan, harnessing the full potential that is heating a room or building is optimal. And you can actually calculate the Seebeck effect, so that you can calculate the voltage times the Seebeck coefficient will be the coefficient of a metal that varies, its metal property, and then times the temperature. So you notice right now, since the temperature is, there's a zero difference, it's not rotating whatsoever, so that's why. So we're going to do a demonstration soon on the stove, and we're going to witness it going more quickly. So we'll go there now, actually. So we'll go to the stove here. And I will heat the base of the fan. So you can see there, I think you can see it, the base is getting hot. I'm choosing the wood stove, the stove right now, because it's just quicker. Just for this experiment, it's more practical. So the purpose of this demonstration is to witness the fans of the blade rotate after the bottom portion is heated and the top portion of the fan is left cool. The materials included are basically the wood stove, or the stove I should say, stove oven, the eco fan. So the procedure is just heating the base of the fan in order to witness that the Seebeck effect and thermoelectric effect will come into play. So the observation we should try and notice now is that there isn't very big of a temperature difference between the two metals. So there isn't any electricity, but once the module is heated and the top is cool, you will notice that the blades of the fan will begin to rotate on its own. One thing to note for this experiment as well is that, there you go, so you see it's already starting to rotate, and I'll actually turn that down. That's quite quick. With an oven, or with this fan I should say, heat isn't, there's going to be heat throughout the wood stove oven anyway, but for basically this experiment you can't feel it, but I can actually feel slightly more of a warm breeze, and that's what it's meant to do. Is it's supposed to give someone in the room a more horizontal feeling of heat, because heat will just rise from the wood stove oven up. And this effect, if you're sitting down in a lawn chair, or a chair I should say, in front of the oven, you'll feel heat there. The same effect is true about the opposite of the Seebeck effect. This was found out by French physicist Jean-Charles Athens Peltier in 1834, where an electric current maintained in a circuit of two dissimilar metals resulted in heating in one metal and the cooling in another. And that basically gives you the refrigeration effect, as you can see in the background there. So this figure here, you can basically see without a fan, you basically just have heat rising into the top portion of the room. And this, with the fan, you can see that heat is being dispersed on a more horizontal angle for a user. So it basically creates more of a thermal effect. And thank you, and I hope you enjoyed this video.